It feels like every single week there's some new leap forward in AI that
Yeah.
just, it makes your jaw drop.
Doesn't it just? Yeah.
We're talking models like GPT-4o, Llama 3, Claude 3.5, DeepSeek-V3.
Yeah.
Really feels closer to, AGI sometimes.
Absolutely. Yeah. And this breakneck pace, it relies fundamentally on scale, right?
Mm.
Massive data, huge models.
It's compute.
Exactly. Huge compute. But there's a catch, a pretty big one, actually, the
Yes.
hardware.
We're hitting some serious bottlenecks. I mean, memory capacity, raw compute power, and maybe the biggest one, the connections. How fast you can shuttle data between all those chips and servers.
Right. The physical limits are starting to bite. And that's exactly what we're digging into today. We've got this really fascinating paper from the DeepSeek AI team, the folks behind DeepSeek-V3.
Mm.
And it's basically a deep look at the hardware headaches they ran into building that model and, crucially, what they think needs to happen next with AI hardware. Yeah, it's not just here's our cool model paper. It's more like, here's how we built V3 because of the hardware, and here's what that taught us about designing future systems. It really drives home this idea of hardware-software co-design.
Co-design, yeah. They didn't just throw software over the wall?
Nope. They designed the model with those hardware realities baked in, and then use that whole experience to suggest, concrete things for the future.
Okay, so our mission for this deep dive. Let's unpack how DeepSeek V3 was kind of engineered around these hardware limits and figure out the key takeaways from the authors for what comes next in AI systems. Ready to jump in?
Let's do it.
Okay, so first up, something anyone training these huge models bumps into.
Yeah.
Memory wall. It's like these LLMs are just unbelievably thirsty for memory.
Oh, absolutely. The paper states memory demand is growing over, 1,000% per year? It's kind of nuts.
1,000%. While the actual high-speed memory, like HBM, that's growing way slower.
Way slower, under 50% per year. So, yeah, you can spread the load across more nodes. Multi-node parallelism helps there, but you have to get smarter about using the memory you've got within the model itself. It's just essential.
The DeepSeek V3 did that in a couple of key ways, right, in the model design. First one they mentioned is load precision.
Yep, using FP8, so floating point 8-bit precision. Standard is often BF16, bfloat 16.
Right.
Just moving to FP8 basically cuts your memory needs for weights almost in half right off the bat.
Which is huge, just bam, half the memory. But okay, they also zoom in on this other bottleneck, the KV cache, especially during inference, when you're actually using the model.
Yes, the KV cache.
Can you break that down? What is it, and why does it become such a memory hog?
Sure. So imagine you're talking to the AI, right? For it to make sense of what you're saying now, it needs context from what came before.
Conversation history.
Exactly. It stores key bits of information, these key and value vectors from previous words or tokens in this cache, the KV cache. So it doesn't have to recompute everything constantly.
Okay, saves computation. Sounds good.
It is good for latency and keeping context, but the longer the conversation, the more tokens you process, the bigger that cache gets. It just grows and grows linearly.
Okay, so it balloons over time.
It does. And here's the kicker. It changes what the bottleneck is. The main attention calculation often involves big matrix multiplications, GEM. That's usually compute bound. My GPU is busy doing math.
Right.
But dealing with that growing KV cache, that often involves matrix vector multiplications, GEMV. And that becomes memory bandwidth bound. The GPU ends up waiting around for data to be fetched from memory, not actually crunching numbers.
Hitting that memory wall again. But this time during inference because the cache is just too big or too slow to access. So how did DeepSeek V3 tackle that specific problem?
They use this technique, multi-head latent attention, MLA.
Okay.
So instead of caching the full raw key and value vectors for every single attention head, and there can be many heads, MLA learns to compress all that information down into a much smaller latent vector, like a summary.
A compressed representation of the important stuff.
Precisely. And that compressed vector is what gets cached, not the full KV pairs.
And the difference is significant.
Oh, yeah. According to their paper, DeepSeek V3 with MLA needs only about 70 kilobytes per token for its KV cache.
70 KB. Okay. Compared to
Llama 3.1405B using grouped query attention, which they say needs around 516 KB per token, or even Quen 2.572B still needing 327 KB.
Wow. Okay, 70 versus 300 or 500 KB. That's a massive reduction in memory needed just to hold the context.
It really is. It directly attacks that inference memory bottleneck. Now, they do mention other ways people try to reduce the KV cache.
Right, like sharing KVs across heads like GQA or MQA.
Or limiting the history window.
Exactly, or even quantizing, compressing the cache itself. But for V3, MLA was their core approach here, finding smarter ways to represent that context.
Okay, so that tackles memory. But DeepSeek-V3 is also known for its mixture of experts architecture, their DeepSeek MOE. And that seems key for cost effectiveness. How does MOE help with costs? Right, MOE. The basic idea is you build a huge model overall, but it's made up of many smaller, specialized subnetworks. We call them experts.
Okay.
And for any given piece of input, like a word or token, you don't run the entire massive model. Instead, a little routing mechanism directs that token to only a small number, maybe 2 or 4, of these specialized experts.
So most of the giant model is actually sitting idle for any specific calculation.
Exactly. DeepSeek-V3, for instance, has a whopping 671 billion total parameters. Sounds enormous.
Yeah.
But for any single token, it only activates around 37 billion of those parameters. Compare that to a standard dense model like, say, Quen72b or a hypothetical Llama 405b, where pretty much all parameters fire for every token.
So the computation per token is much lower.
Way lower. They put numbers on it. DeepSeek-V3 MOE needs about 250 gigaflops per token. A 72 billion dense model, around 394, that 405 billion dense model, over 2,400 gigaflops per token.
Okay, that's a huge difference in computational load per step.
Which directly means lower training costs, less energy, maybe less hardware needed overall. It's a big efficiency win.
And does that translate to inference too, like for someone running it not in a giant data center?
Yeah, definitely. Because the active memory and compute needed per request is much lower, you can potentially run these very large MOE models on more, well, accessible hardware. They give an example with DeepSeek-V2, which was 236 billion total, but only activated 21 billion for inference.
Okay.
They say that allowed it to run at around 20 tokens per second on just a regular PC, assuming it has some AI accelerator chips, so guess. Whereas a dense 70 billion parameter model might really struggle on that same hardware, maybe single-digit tokens per second.
That's really interesting. The architecture itself makes it feasible on non-supercomputers.
Right, and they even mention using an inference engine called K-transformers, allowing the full DeepSeek-V3, the big one, to run on a server costing maybe around $10,000, still hitting about 20 tokens per second.
$10,000 isn't exactly cheap, but it's a world away from a multi-million-dollar cluster.
Exactly. So MOE, when you optimize it right, really does seem to open doors for broader access, not just the hyperscalers.
Okay. Memory efficiency, check.
Yeah.
Cost effectiveness through MOE, check. What about speed? Just getting those answers out quickly during inference, that's crucial. How did V3 get faster?
They hit it from a couple of angles. First, during training, optimizing how computation and communication overlap, using something they call dual pipe.
Dual pipe?
Yeah.
That sounds like trying to keep the GPUs busy all the time.
Pretty much. It's a strategy using dual microbatches. Think of the training process broken into tiny steps, microbatches.
Right.
While one microbatch is doing its forward and backward computation passes, the next microbatch is handling its network communication, maybe sending gradients, or in MOE, exchanging data between experts.
Ah, so you hide the waiting time for the network behind the actual math work.
Exactly. Keep those expensive GPUs crunching numbers as much as possible, maximizing utilization.
SAR. Okay, and then there's this other technique they talk about, multi-token prediction, MTP. That sounds intriguing.
Yeah, MTP is pretty cool. It builds on ideas like speculative decoding. Normally, these models generate one token, then the next, one at a time. Autoregressive.
Standard way, yeah.
MTP adds lightweight prediction modules on top of some existing layers in the model. These little modules try to guess what the next few tokens after the main one will be. And they do it really cheaply, computationally speaking.
So the main model predicts token A, and these helpers quickly guess B, C, D.
Kind of like that, yeah. Then you verify these guesses, B, C, D, against the full model, which you can do in parallel if a guess is right.
You get multiple tokens for the price of roughly one step.
Bingo. And they report really good results, like an 80-90% acceptance rate for the second token prediction. They say this boosted generation speed by about 1.8 times compared to not using MTP.
Wow, nearly doubling the speed.
And it has a nice side effect. It helps you batch inference requests more effectively, which again improves hardware utilization, especially important for MOE models.
Okay, MTP sounds like a big win for inference throughput. But the paper points out a hard limit, especially for MOE inference speed, the network itself.
Yeah, this is critical. For MOE, you have that expert parallelism step. Tokens need to get routed to the right expert GPU, processed, and then the results gathered back. This involves an all-to-all communication pattern across the network.
All the nodes talking to all the other nodes, basically.
Pretty much. And that step is incredibly sensitive to network bandwidth and latency. The paper gives some stark theoretical numbers, like on a standard cluster using 400 gigabit per second InfiniBand.
Which is fast.
It is fast. But the theoretical limit for that all might cap your throughput at around, say, 67 tokens per second per GPU, just because of the network communication.
Okay.
But then they contrast it. Imagine something like NVIDIA's newer GB200 system, which has this super high bandwidth NVLink between chips in a rack 900 gigabytes per second. Suddenly, that theoretical limit jumps to maybe 1,200 tokens per second.
Whoa. Okay, that's a massive difference. It really highlights how the physical network fabric becomes the ultimate speed limit for these distributed MOE models.
Absolutely. It's not just about the GPU compute anymore. The interconnect is king.
Let's circle back to that low precision idea, FP8, but specifically for training,
Right.
because they learned some important lessons there that led to suggestions for future hardware.
Right. DeepSeek-V3 is significant partly because it's one of the first really big open source models trained using FP8 mixed precision. That wasn't easy. They mentioned close collaboration between their AI folks and hardware teams, plus needing special tools like DeepGM.
So they proved it's possible to train huge models in FP8 and keep the accuracy up.
They did, yeah. But you need careful techniques, especially something called fine-grained quantization. But they also hit some walls with current hardware when using FP8.
What kind of walls?
One main one was the precision used for accumulation inside the tensor cores. These are the specialized math units on the GPUs, like on NVIDIA's Hopper chips. When you multiply lots of FP8 numbers together and add them up, the register that holds the running total, the accumulator, might not have enough precision. Small errors can build up over many operations.
Potentially messing up the training stability for really big models.
Potentially, yeah.
Yeah.
Especially very deep models or long training runs. The other limitation was around actually doing that fine-grained quantization efficiently.
What's the issue there?
Fine-grained means applying scaling factors not just once per big tensor, but to small blocks or tiles of data within it. On current hardware, often what happens is the tensor core does the initial FP8 multiplication,
Right.
but then the result has to be moved out to the regular CUDA cores to apply the scaling factor and convert it back before the final accumulation. This shuffling data back and forth, it adds overhead. It slows things down.
Okay, so based on running into those issues, what are they asking hardware makers to do differently?
Well, for the accumulation, pretty straightforward. Just give us more precision in those accumulator registers. Maybe FP32 or make it configurable. Just something more robust for these massive sums.
Makes sense. And for the quantization overhead?
They strongly suggest native hardware support. Build the ability to handle those fine-grained scaling factors directly into the tensor cores. Let the tensor cores receive the scaling factors and apply them internally without that costly detour to the CUDA cores.
Streamline it right in the specialized hardware.
Exactly. Keep the data flowing efficiently within the math units.
They also mentioned experimenting with another format, log FMT, just for network communication.
Yeah, logarithmic floating point formats. Kind of an interesting idea. Use the same number of bits as FP8, maybe, but distribute the representable numbers logarithmically instead of linearly.
Why do that?
It can give you better precision for a given range of numbers compared to standard FP8. They thought it might be good for sending things like weight updates or the combined expert outputs during MOE communication.
But it sounds like they didn't end up using it in V3.
Correct. The format itself looked okay, but actually encoding data into logFMT and decoding it out on the current GPUs, it just added too much overhead, especially if you tried to fuse it directly with the all-to-all network operations. It caused GPU bandwidth issues, register pressure.
Ah, so another case of a neat algorithmic idea hitting practical hardware limits.
Yeah. And the suggestion follows directly. Build native hardware support for this stuff. Put compression and decompression units, maybe for FP8 or custom formats like logFMT, right into the network interface hardware.
Offload it from the main GPU.
Exactly. Save the GPU cycles, minimize the actual network bandwidth needed, and just make the whole pipeline smoother.
Okay, let's zoom out a bit from specific formats to the overall cluster architecture. The paper talks about the specific NVIDIA H800 nodes they used and how that hardware choice really shaped DeepSeek-V3's design.
It absolutely did. It's a key example of that co-design principle. So the H800 nodes they had, compared to the, say, H100, they actually have less NVLink bandwidth within the node, connecting the GPUs inside the server. It was 400 gigabytes per second versus maybe 900 on an H100.
Less speed inside the box. That seems counterintuitive.
Well, to compensate for that reduced scale-up bandwidth, The H800 was designed with more connections for scale-out, multiple 400 gigabit InfiniBand network cards per node, specifically for talking between servers.
Ah, okay. So the trade-off was less speed internally, more pipes externally?
Exactly. And that specific hardware profile, slower inside, faster outside, relatively speaking, directly drove how they parallelized DeepSeek V3.
How so? What'd they do differently?
Because the intranode NVLink was slower, they tended to avoid using tensor parallelism, or NTP, much during training. TP slices up individual calculations and needs really fast communication between the GPUs working on those slices.
Which the H800 wasn't ideal for.
Right, so instead, they leaned more heavily on pipeline parallelism, PP, using things like that dual pipe technique we mentioned to keep things flowing. And critically, they focused on accelerating expert parallelism, EP, for the MoE parts. They developed something called DeepEP, specifically optimized to use those multiple fast InfiniBand NICs for the heavy all-to-all communication needed between nodes.
Okay, tailoring the parallelism strategy to the specific strengths and weaknesses of the H800 hardware.
Precisely. They managed to get over 40 gigabytes per second of all-to-all bandwidth per GPU using that DeepEP setup on the H800s.
And that hardware reality also led to that clever node-limited routing for MoE, didn't it?
Yes, exactly. They knew that even with multiple NICs, the internode InfiniBand communication was still effectively slower than the intranode NVLink communication, maybe a 4-to-1 ratio in effective bandwidth for their workload.
Okay.
So when their MoE routing mechanism had to pick which experts to send a token to, the top K selection, they didn't just pick the best experts anywhere in the whole cluster, they constrained it. They grouped experts physically by server node, and the routing algorithm was designed to only send tokens to experts located on a limited number of other nodes, say a maximum of 4 different nodes out of an 8-node group, for example.
Oh, so you minimize crossing that slower internode boundary. You jump to the right neighborhood of nodes once.
Right, and then once the token arrives at those target nodes, you use the faster intranode NVLink to efficiently distribute it to the specific expert GPUs within those nodes.
That's smart. It's designing the algorithm specifically to work around that known hardware bottleneck, the slower link between servers.
It's a perfect example of hardware-aware algorithm design, mitigating that bandwidth disparity.
The paper then broadens this out, talking about the convergence of scale-up connections inside a node like NVLink and scale-out connections between nodes like InfiniBand or Ethernet. They point out some current inefficiencies.
Yeah, right now, a lot of the burden for managing network traffic, even just forwarding data between the scale-up and scale-out fabrics, falls on the GPU's main compute units, the SMS.
The streaming multiprocessors, they're doing network management.
Often, yes. Things like moving data buffers, managing the transport protocols, even doing reduction operations when combining data from different nodes. It's all work that takes SMs away from doing the actual AI math. They estimate it could be consuming up to 20 SMs on an H800.
That feels really wasteful, using your primary compute engines for plumbing.
It kind of is. They do note that asynchronous communication models like RDMA, which can bypass the CPU and sometimes the SMs, are generally better, especially for things like online inference.
So what's the vision for fixing this? How do we get better convergence?
Well, they suggest things like unified network adapters, NICs, or maybe dedicated I/O chiplets that connect smoothly to both the intranode fabric and the intranode network. These could even act as basic switches themselves.
Taking the load off the SMs.
Exactly. And maybe even having dedicated communication coprocessors or I/O dies specifically designed to handle all these network tasks, forwarding, broadcasting, reductions across both networks efficiently. Plus, critically, building hardware-level synchronization primitives. Like memory semantic communication with built-in ordering guarantees, maybe using acquire-release semantics at the hardware level. This avoids needing complex, slow software mechanisms to make sure data arrives consistently and in the right order. They mention new protocols like UEC, UA, Link, UB as steps in this direction.
Okay, let's shift focus slightly to the network topology itself, how the whole cluster is physically wired together. They use something called a multi-plane fat tree, or MPFT.
Yes, for the big DeepSeek-V3 training cluster, they deployed an 8-plane, 2-layer fat tree network using InfiniBand. The core idea of MPFT is that each GPU and its network card basically live on their own separate plane of the network.
8 parallel network planes.
Kind of, yeah. It's a variation of a multi-rail fat tree, MRFT. The advantage is theoretical scalability, they say. This two-layer design could potentially scale beyond 16,000 GPUs. Plus, it might offer benefits in cost and maybe latency compared to traditional, denser three-layer fat trees.
What are the specific upsides of wiring it this way?
Well, being related to MRFT means they could use existing, well-optimized communication libraries like NCCL, which is a big plus. Cost-wise, their analysis, Table 3 in the paper, suggests MPFT is pretty efficient. Similar cost per connection endpoint to things like SlimFly and much cheaper than a full three-layer fat tree.
Okay.
It also offers some traffic isolation because congestion on one plane is less likely to directly impact other planes. Potentially lower latency as traffic might cross fewer switch hops than in a three-layer design. And maybe better robustness, especially if you use multi-port NICs for redundancy across planes.
Did it work out in practice? Did the performance match the theory?
Yeah, their tests seem to validate it. They ran benchmarks simulating the all-to-all patterns needed for MOE and found the MPFT performance was very close to a standard multi-rail setup. And importantly, it achieved that target of over 40 gigabits per GPU, nearly saturating the NIC bandwidth. So yes, it delivered for the DeepSeek-V3 training.
But they did mention a current latency issue with cross-plane traffic.
Right. If data has to jump between planes, currently it has to go through that intranode forwarding step using the SMs, which adds latency. This just reinforces their earlier point about needing better hardware convergence to handle that seamlessly.
You mentioned latency is super critical for MOE's all-to-all. The paper compares InfiniBand IB versus RoTE RDMA over converged Ethernet.
Yeah, this is a key practical point. InfiniBand generally offers lower latency. Their measurements showed for small messages, IB was around 2.8 microseconds latency if the communication stayed within the same leaf switch, maybe 3.7 microseconds if it had to cross to another leaf.
Okay. And RoTE?
RoTE was higher, around 3.6 microseconds same leaf and 5.6 microseconds cross leaf. So IB definitely has a latency advantage, which is really good for those synchronized EP communications.
But there's always a but. IB hardware tends to be pricier, right? And maybe doesn't scale quite as large?
That's the trade-off, exactly. IB switches cost more per port, and they often have fewer ports per switch compared to high-density Ethernet switches. This limits how big you can build a single unified IB fabric compared to what you can do with RoTE. So making RoTE better for AI is really important for building massive cost-effective clusters.
So what do they suggest to improve RoTE for these AI workloads?
Several things. One is specialized low-latency RoTE switches, maybe hardware that strips out some general-purpose Ethernet features not needed for AI traffic. They mention things like Craze Slingshot or Broadcom's AI forwarding header as examples.
Okay, purpose-built hardware.
Right. Another big one is smarter routing policies. Standard ECMP routing often performs poorly because AI traffic isn't always random, leading to overloaded links. They show adaptive routing, AR, which dynamically shifts traffic based on congestion, works much better. Figure 8 in the paper illustrates this.
Dynamic routing instead of static.
Exactly. And finally, better traffic isolation and congestion control within the switches and network. Things like more hardware priority queues, virtual output queuing, VOQ, maybe congestion control based on round-trip time, RTT, to handle the bursty nature of AI traffic better and prevent congestion collapse.
They also mentioned using InfiniBand GPU Direct Async IBGDA. What's that about?
Yeah. That's a technique specifically for reducing latency. Normally, the CPU acts as a middleman for network operations initiated by the GPU. IBGDA lets the GPU manage the network control and data transfers more directly, bypassing that CPU proxy.
Cutting out the middleman.
Basically, yeah. Avoiding that round trip to the CPU saves precious microseconds, which really adds up for the kind of small, frequent, latency-sensitive messages common in AI training and inference.
Okay, shifting gears a bit. The paper brings up system robustness. How do you keep these monster clusters running reliably?
It's a massive challenge. You've got thousands of GPUs, miles of cables running flat out for weeks or months. Things will fail. Links glitch, nodes die, GPUs throw errors, memory gets ECC corrections. That's almost expected.
Right. Failures happen at scale.
But the really scary thing they highlight is silent data corruption, where an error occurs, maybe a bit flips somewhere, but it's not caught by the standard error correction codes. It just silently damages your model weights or activations.
And you might not know until weeks later when your multi-million-dollar training run is ruined.
Exactly, it's a nightmare scenario.
So what are the suggestions for improving robustness?
They argue for hardware with more advanced end-to-end error detection capabilities built in, going beyond basic ECC on memory, maybe adding checksums or other redundancy checks throughout the data paths, and just as importantly, providing users with really comprehensive diagnostic toolkits.
Tools to let the users check the system themselves.
Yes, tools to actively verify the integrity of the hardware and detect potential silent corruption before it ruins a long job. Building trust in these huge, complex systems means giving users the power to validate them.
We've talked a lot about GPUs and networks, but the paper throws a flag on the CPU too, saying it can still be a bottleneck.
Yeah, easy to forget the CPU amidst all the accelerator focus, but it's still coordinating everything, managing I/O, handling the overall flow. A key bottleneck they point out is the PCIe bus connecting the CPU to the GPUs.
The main data pipe between them.
Right, moving big chunks of data like model parameters or maybe parts of the KV cache if it spills over across PCIe can be slow. And to even saturate the PCIe bandwidth you have, you need incredibly high CPU memory bandwidth, feeding it, they estimate, maybe 1 terabyte per second per node.
Wow, that's a lot of memory bandwidth just from the CPU side. And single core speed still matters too.
Definitely. For tasks that are latency-sensitive, launching kernels on the GPU, handling network interrupts quickly, coordinating parallel tasks, you still need high clock speeds, ideally over 4 gigahertz according to them. Plus, you just need enough CPU cores per GPU to manage everything, especially with complex chiplet designs adding overhead.
So how do we fix the CPU bottleneck?
Tighter integration is one path. Direct CPU-GPU interconnects like NVLink between CPUs and GPUs, or AMD's Infinity Fabric bypassing PCIe, or maybe integrating CPU cores directly into the scale-up domain alongside the GPUs.
Bringing them closer together.
Yeah, plus acknowledging the need for that extremely high CPU memory bandwidth, and ensuring future CPUs don't just add cores, but also keep pushing single-core frequency for those latency-critical tasks, while providing enough cores overall.
Looking ahead, it feels like the paper envisions much more intelligent networks for future AI systems.
I think that's fair. Not just faster pipes, but smarter pipes. They talk about things like co-packaged optics, bringing optical connections right onto the chip package for massive bandwidth gains and better energy efficiency.
Getting rid of electrical limits.
Right. Gives you incredibly high bandwidth between logic and memory, very low latency, and potentially quite large capacity, too. They think this could be particularly useful for MoE inference, which often gets bottlenecked by memory access. They also briefly mention system-on-wafer concepts for ultimate density.
And they touched on memory semantic communication again, and this tricky problem of data ordering.
Yeah, the idea of just using simple load and store commands to communicate between processors or nodes is really appealing. It's easy for programmers. But the problem is ensuring that updates happen in the right order, especially when multiple things are happening concurrently.
You need to make sure read happens after write, etc.
Exactly. Today, you often need explicit software instructions, fences, or barriers to enforce that order, but these add latency, they stall the pipeline. You see similar issues even with message-based RDMA sometimes.
So the fix is build ordering into the hardware.
That's the suggestion. Hardware support for guaranteeing ordering. Maybe expose it through programming concepts like acquire and release semantics, but have the hardware itself enforce it efficiently at the receiver end. They mention a concept called region acquire release, RAR, as one possible way hardware could do this with low overhead.
Okay, one last area they see opportunity in. Pushing more work into the network hardware itself, specifically computation and compression, especially for MoE.
Right. During those MoE all-to-all stages, there are opportunities. When you dispatch a token to multiple experts, that's basically a multicast. Maybe the network hardware can help replicate packets efficiently.
Okay.
And when you combine results back from the experts, that's a reduction operation. Conceptually, maybe the network could do some aggregation in flight, though they admit that's trickier due to the complex and imbalanced nature of MoE traffic.
And bringing back the compression idea here, like with log FMT.
Exactly. Natively building support for compression and decompression, maybe using standard formats like FP8 or custom ones like log FMT directly into the network interfaces.
Hardware accelerates the decompression.
Yeah. Compress before sending, decompress upon arrival, all handled by dedicated hardware. It saves precious raw bandwidth, which is gold, especially for those bandwidth-hungry MoE training stages.
Okay, wow, that was a lot of technical detail. Let's pull way back. What does all this FP8 accumulators, MPFT networks, memory semantics, what does it actually mean for you listening right now? Why should you care about these deep hardware weeds?
Because the stuff, these seemingly obscure engineering details, they're not abstract problems. They are the absolute foundation for the AI systems that are changing everything around us. Hardware design isn't some separate thing happening over there.
Right.
As this DeepSeek paper shows so clearly, it's fundamentally intertwined with what AI models can actually do. How big can they get? How fast can they run? How efficiently? And maybe most importantly, who actually has the resources and capability to build and use the most powerful AI?
It's not just about faster chips, it's about enabling new possibilities.
Exactly. Pushing AI forward today demands thinking about the algorithms and the silicon together. It's a constant back and forth.
And these limitations, these bottlenecks we've been talking about, they're not just problems, they're also forcing creativity,
Right.
right? Driving innovation in both the software, like MLA or MTP, and spurring these ideas for new hardware designs.
Couldn't agree more. The DeepSeek-V3 project and this paper dissecting it, it's just such a powerful case study for why hardware-software co-design is absolutely critical at the AI frontier.
Yeah.
They really laid out a blueprint. You tackle memory with MLA and FP8, you attack costs with MoE, you boost speed with MTP and smart pipelining like dual pipe, you design your network like MPFT to match your hardware, you build something state-of-the-art that actually works within today's constraints.
But, as they also make incredibly clear, the current constraints are still significant. The challenges are real.
Oh, absolutely. And their suggestions for what needs to come next in hardware unified interconnects, dedicated communication engines, smarter networks, better memory, native low precision support, built-in robustness. It's basically a roadmap, a really exciting roadmap for the hardware innovation that's needed to unlock that next generation of AI.
The future of AI really is tied, maybe more than ever, to what happens at the hardware level.
It feels that way, yeah. Inextricably linked.
Which kind of leaves us with this final thought to chew on. As these LLMs keep getting bigger, potentially exponentially bigger and more complex, how will these hardware innovations they're calling for actually shape things? Who gets to play? Will these incredibly complex, specialized, probably expensive hardware solutions just further concentrate power with a few giants who can afford them?
Or is there another path? Will things like more efficient MoE inference, maybe combined with hardware optimized for consumer devices, actually help spread access? Could it democratize cutting-edge AI rather than centralize it?
Yeah, centralization versus democratization through hardware. Definitely something to keep an eye on as this whole field keeps racing forward.